Hello and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistor, a physics perspective. This is lecture number 57 where we will be further going into the HEMT, high electron mobility transistor, and its modeling technique. You will see this lecture number 56 end of it and 57 starting, there is some overlap in order to have the continuity in the flow of the lecture. So that's the reason you will see some overlap, at least 2 to 3 slides overlap between lecture number 56 and lecture number 57. So we had started with the MVS model, which is basically an HEMT model. As we have already known that basically HEMT is a 2D electron gas, which basically means its rather thin layer of electron is sandwiched between the heterostructure, because of which the charge is referred to as 2D or two-dimensional electron gas or 2DEG. And as a result, the property of that is that it becomes almost like a ballistic phenomena with no mobility. So basically, when we talk about HEMT models, we assume that the mobility of the charge carriers are relatively very high, right, as compared to even bulk semiconductor. And the reason being that there is no scattering or very low scattering, and as a result, you do have a very large current being developed. Now, many a times, industry standard physical models have been already developed, where there is a concept of virtual source methodology being used in order to extract the electrostatics of the HEMT. Now, virtual source is sort of a property where we assume is that we take the source side and we ground it, and we say that that's a virtual source which is acting as a sink of all the charge carriers, and so infinitely large amount of sink is available there in terms of property. The MVS model is basically a charge based model, which means that basically we are trying to find out the total charge, right, the total charge which is embedded within the 2D electron gas. And the methodology which has been followed while doing any device modeling where you have a drift diffusion component available to you is to make the charge, divide the whole channel into smaller pieces, find the charge in each of the pieces, and then you integrate from source to drain to find the total charge. Once you know the total charge, you can substantiate or find the value of the total current which is flowing through the device. Okay, so that was the property through which the physical MVS HEMT models have been developed. Now, however, the physical models don't have independent drain current or capacitance models. What does it primarily means that there's a dependency between the capacitance, which is basically coming out of charge, and the drain current. So they are not two independent models, but they are two dependent models in the physical models which we choose for HEMTs. These are referred to as submodels. Submodels are basically a part of the model such that so you can run in loop. So you want to find out the charge can be fed into the drain current equation, which by itself can generate the amount of current flowing for a particular electrical bias is given, and so on and so forth. Similarly, charge can be found out if you provide the bias and you know what is the doping concentration, and you solve the Poisson equation there and you try to find out the total charge. However, as I discussed with you in MVS models, they are sort of dependent in each other, and which means the drain current and capacitance equations, they are all dependent on each other, which means that you find the capacitance, and from capacitance you try to evaluate the value of the drain current forming in this equation. The drain current equation is given by this equation, which is a standard form of equation even for bulk MOSFET, if you remember properly, where V is the velocity of the charge carriers at any point x. So if I take a MOS device, let me see if I have a graph of that. I don't have it at this stage, but HEMT, if you look, this is my x axis which you see, and this is my y axis, right? So I try to find out the velocity at any point x within the channel, multiply that with the inversion charge per unit area for that particular point x. So if this is x, I take small delta x value between this point and this point and try to find out the charge. I refer to it as QI charge, which is basically the inversion charge per unit area. Multiply that the width of the material or the HEMT, and then multiply with NGF, a constant, right? Now you can also have a width quantized or a width normalized drain current. Then what you do is that you divide this IDS by this W, and what we get from here is we get NGF multiplied by QIX multiplied by V times X, right? Okay, if you go back to your very basic equation of mobility, then you very well know that the velocity of the charge carriers is referred to as mobility multiplied by electric field, right? Where mu is the mobility and E is the electric field. So if you replace this Vx by its corresponding electric field, then I get this as mu times at that particular point x multiplied by E of x. So therefore, whenever you are going to calculate the current, total current, important parameter which you need to look into is the electric field at that particular point and the mobility at that particular point, right? And the mobility of the charge carriers at that particular point. Now that will vary as you move along in x direction, because as you start moving from source to drain, the mobility of the charge carriers might change because of the varying electric field. Uh, in all respects, we assume that mobility is independent of electric field, but for very short channel HEMTs, that is not true, and mobility becomes basically a function of electric field, right? And when it becomes a function of electric field, higher the value of the electric field, more is the scattering, lower is the mobility. So what happens beyond the point is that as the electric field increases, the mobility drops down such that the multiplication of these two remains constant, and therefore you get a constant current at a certain value of the applied bias. This is the methodology which has been followed when you actually do a device model for HEMT. This is first thing. The second thing is you need to also look into the fact that you have an inversion charge here. This inversion charge Qi, which is a function of x, is basically the charge along strip within the 2D electron gas, right? 2D electron gas. Now this value will go on varying as you move from source to drain, because if you apply the bias. If you remember your basic MOSFET model, let me rub this here and let me write down for you the basic MOSFET equation, which when you take up a source and you have a drain, right? You have a source and a drain, right? And as you can see that as you apply a larger and larger drain bias, the inversion charge density goes on becoming higher and higher towards the drain end, and there's a depletion region available at this particular point, and this is the inversion region, which means that if you take any block at any point, the value of Qi will always go on changing, and that results in the change in the current when you apply a bias. So when you apply a bias, and change in the current is available to you because of the value variations in the value of Qi. In most of the models which you will see otherwise, you will see that the current sometimes are shown as normalized drain current with respect to the width of the charge carrier. So the width does not come into picture in a most decent form of manner. However, if you can see here, the current actually is directly proportional to the width of the charge carriers, right? Where W is the width of the charge carriers, and therefore IDS is directly proportional to the width of the charge carriers. And higher the value of the width, obviously more will be the current, because more will be the charge. But generally in many of the research papers or in books, we see that it is normalized with respect to width, and the width is divided into the left hand side, and such that the width does not come into picture, and therefore there's a constant term which always comes into picture and gives me the value of IDS. Okay. Now, so this is the drain current equation for the HEMT model which we choose. This is what I was saying, that if I assume that at any point within the channel, right, psi s is the potential, psi s is the surface potential at any point in the channel. So this is my channel, let us suppose my 2D electron gas is confined within this shaded region. This is my shaded region which has got my 2D electron gas, and let us suppose this is my x, and the potential at this particular value of x is psi of x, let us suppose. Then we all know that the electric field is the first derivative of the potential. So what we do is that we do d psi of x dx. That is the electric field in the horizontal direction, right? Psi x d psi x dx is the electric field along the x direction, right? and therefore I can write down velocity of the charge carriers V as equals to mu times E of x. E of x is the electric field in the x direction, where E of x can be written as d psi x dx, right, and multiplied by mobility. I am assuming here again that the mobility is constant mobility, which we are assuming here for the time being. And therefore, if I take this equation and place it back into this equation of the current, then we get the current to be equation to be equals to this value, that it is W times ngf multiplied by qi multiplied by mobility into d psi of x of dx. However, if you remember correctly, that the charge carriers movement within the channel is actually a function of both Ex and Ey. Ex is the electric field in this direction and Ey is the electric field in this direction. So, the effective electric field which you will feel, E effective, will be given as Ex square plus Ey square, square root of this one, square root of this one. This is the effective electric field. So, a charge carrier will actually feel the electric field equal to this value, right. That will result in the effective electric field. This effective electric field, when multiplied by mobility, gives you the velocity of the charge carriers at that particular point. Now, if I assume that velocity saturation has already been taken place, which means that the saturation of the velocity is there already, which means that the velocity, if you remember very carefully basic MOSFET equations, then you will understand and appreciate that initially when you go on increasing the electric field, if you plot velocity versus electric field on the x axis, then the graph becomes something like this, right, which means that the electric field increases, the velocity goes on increasing for low values of electric field, right. This is my low value of electric field, let us assume. Then as the electric field goes on increasing, the velocity goes on increasing, which is by first principles, which we already know. But please keep in mind, as the velocity goes on increasing, the number of scattering also goes on increasing, because you are encountering the electrons are encountering more number of carriers at the more number of ions there, fixed ions there, and so scattering becomes larger, and therefore there is a drag also becomes increasing, and therefore it does not simply go on increasing linearly, right. It increases in a linear fashion, then it becomes non-linear in nature because of that drag, and the time comes when the drag becomes exactly equals to the force due to the electric field, and that's where the velocity becomes constant. So, this is the meaning of the constant velocity saturation. So, velocity saturates basically, and therefore the currents also saturate somewhere near this one. Keeping that in mind, what people have shown through all large number of research papers, that this quantity d psi x dx, which is the electric field, can be written as in a this manner. This is what they can be written, of course. So, if you look at the top, it is d psi x dx, which is still the same. However, if you look at the bottom side, you have a quantity known as Vsat and mobility. Vsat is the saturation velocity of the charge carriers, and mu is the low field mobility of the charge carriers, and it depends upon a factor beta. Now, if you see quite interestingly, this is basically, if you look carefully, this beta will actually get cancelled out from a purely mathematical point of view, and therefore what I get d psi x dx, right, dx divided by 1 plus d psi x dx, right, divided by Vsat by mu, right, Vsat by mu you will get. Now, if you look at this, the whole dimension of this should be equals to d psi x dx, then only you will have the proper current available to us in a sense. And if you look very carefully, that is coming also, because d psi dx is electric field, V is equals to mu into E. So, this will be mu into E, this mu gets cancelled out. So, I have electric field available with me, and therefore typically the left value is only electric field, because this electric field at the bottom gets cancelled out, and therefore dimensionally this seems to be a correct equation. And depending on the value of Vsat, which is the saturation velocity, So you see, quite interestingly, if the saturation velocity becomes very high, or the quantity becomes very high, which means that this quantity becomes very large, it primarily means that the denominator becomes very large, this becomes very large, which effectively means this becomes very small, and therefore this component becomes very large, right, which means that higher the velocity, saturation velocity is, more will be the electric field available to you, which is makes sense also, because see, higher the saturation velocity implies that your electric field has to be very high at that particular point to maintain that value of electric velocity saturation, in a sense, in that particular area. That's the reason you get d psi x dx, and if you multiply that with mu multiplied by qi, ngf and w, I get the total current IDS. So let me rub this portion and just recapitulate what we did in this case. What we did in this case was, we tried to find out the total drain current as a function of the applied bias for a HEMT, which is almost the same as just like as we do it in a bulk MOSFET. Here we have assumed that the mobility to be constant, and we have also assumed that it's a one dimensional electric field in reality. However, we might have a two dimensional electric field available to us when the dimension of the devices are very small. When the dimensions are small, then you will have the effective electric field to be root square of the individual electric field in the x and y direction. So this is the overall picture which we get for the drain current equation, in a sense, for the velocity saturated case. I would recommend that you please take care of the non velocity saturated case. This you can do it as an assignment, non velocity saturated case. You try to find out the drain current equation in this case when you don't have the non velocity saturated case, right. It is not the velocity saturation, but some other principle which tries to make the current go to a constant value. So that you need to find out in your case, and that's sort of an assignment for you. Now whenever you try to find out the charge, this we have already seen in our previous lecture. I want to just quickly take care of this charge and the capacitance equation. In most of the MOS devices or even HEMTs, we assume that the device is symmetric in nature, which means that if you interchange source and drain, right, if you interchange both sides, then we assume that there will be no change in the current. However, in reality that is not true. The reason for that is that the charges which are available at individual points within the channel, they don't get separated out under bias condition in a symmetrical fashion, which means that if you take a, let us take you take a MOS device and you have a source and drain, and you apply a bias here, say plus some value 0.5 volts, and then you interchange and have another case where the source is basically having 0.5 volt and this is grounded, then the amount of charge which is located on the source side and the amount of charge located on the drain side for this case and this case will not be symmetrical in nature. They will be asymmetric in nature, as you can see it from the equations which are given here, right. And this is known as charge partitioning techniques which is available. Now the charge density, charge per unit area basically. So what you do is that if you take this is the total charge, if you go into the denominator, then I get as Qs, and therefore this is Qs by W into L is basically my charge density, which depends upon the inversion charge on the source side, drain side in this fashion. A complicated equation which is available to us here. And then this is also an equation which is available to us here. Obviously, as you can see, they are not exactly symmetric in nature. There is an asymmetricity available between the two, right. As a result, what happens is that if I assume that QIS and QID are not equal, obviously which is not, QIS is the amount of inversion charge on the source side, number of charges or charges on the source side, at the source side, and QID is the number of charges per unit area on the drain side, and since they are not equal, because the depletion region thicknesses are not equal when you apply a bias, you all know that. Same thing happens in the HEMT, that they are not equal and therefore their charges are totally different from each other, the source side and the drain side per unit area. However, we also know that gate to source and gate to drain capacitances are given by dq dv, right, charge per unit voltage which you see. and CGD is the gate to source for HEMT, and CGD is gate to drain for HEMT, and they depend upon the total charge upon the biases which you apply in this case, right? And that is from where we can get the value of CGS. Now, let me come to another model therefore, and this is known as the DynaFET GAN HEMT model, and this is a machine learning based model which is basically applied to gallium nitride based HEMT models. Uh, uh, Typically we use here artificial neural network HEMT model to do a feed forward neural network uh, iteration, right? Typically there are 2 to 3 hidden layers, and typically they help you to construct a nonlinear current capacitance equations. This was actually proposed initially by Keysight. This was done by Keysight, and then this ANN based HEMT model typically adopts this feed forward neural network methodology, and it continuously learns by doing a simple architecture of 2 to 3 hidden layers. The weights go on changing as and when available to us. However, in both the cases we will require a large amount of experimental data in order to suffice this ANN model. Now, both bias dependent and temperature dependent current and charges are extracted by this DynaFET model, where ANN is used to model the equation, and the modeling equations are given by this equation. Looks complicated, but it's actually very easy to understand if you look carefully. So you see there are two components of the current which we are trying to do in a GAN HEMT model. First is a gate current, which is again a time dependent gate current, and we have a time dependent drain current here. So I have this gate current at this particular point here, and I have this drain current at this particular point. Now, if you look carefully here, this gate current, which is a function of time t, is equal to the gate current which is depending on the value of the DC bias, not the DC bias, the transient you are giving a gate to source and drain to source. So, gate to source and drain to source transient biases, and function of certain other equations which are Tj, phi 1, phi 2, phi 2 t, right? And it also depends upon how the rate of change of the gate charge with respect to time t, which is basically a function of again gate to source, gate to drain, applied phi 1, phi 2 t, and the value of Tj, right? Same thing happens for Id. So this was for Ig and this is for Id. Only change which you therefore see is that this Qg is replaced by Qd. So Qd is the total amount of drain charges, or the total amount of charge available on the drain side, and Qg is the total amount of gate charge which is available to me on the gate, just near the gate, which you see. And this is based on bias and temperature dependent current and charges which is used. And this is the expression which typically we follow for the case of a DynaFET GAN HEMT model. The last model which is there is an advanced SPICE model for GAN HEMT models, and typically the CMC candidate, which is a compact model candidate for industry standardization, is an ASM HEMT model which was developed at IIT Kanpur, and we also have this GAN FET model which was developed at MIT. And both this ASM GAN FET model is a surface potential based model, which means that if you are able to extract the surface potential at individual points in the channel, you will be able to extract the value of the HEMT model. What is the advantage of surface potential based model is that it is highly accurate, first of all, because you are trying to find out the surface potential at individual points. You can therefore do a backtracking, get the value of the total charge and the capacitance. Second thing is that it is highly scalable, which means that if you scale the model up or down in terms of structurally and therefore with respect to bias, the charge partitioning allows you to do a proper scaling down or scaling up of the charge equations. There are obviously less number of parameters to deal with, and therefore computationally more intensive and more easier to do, and it's easier parametric extraction. And typically, because of the continuity, we generally use single equation for all the regions. So what happens is that single equation becomes more prevalent at particular region of operation and becomes less prevalent at the other regions of operation, depending upon the place at which you are doing the calculation, right? So this is the advantage of the SPICE model. So what we have learned in this lecture is of course understood the basic modeling of an HEMT, GAN based HEMT, and then we looked into two types of model. One was ASM model, and which is surface potential model, and an ML based DANA-FET GAN model, which was developed by Keysight. So these two models we have just seen. In our subsequent lectures, we will further look into vertical HEMT and other forms of HEMT as far as this course is concerned. Thank you for your patient hearing.